You ever notice that some people have some annoying tics when they're speaking in front of large groups or even small groups? I sure hope I don't have any of those things. Okay. Let's do some notes here. Quick review of what a function is. It's a correspondence between two sets A and B as a function of A to B, if and only if each member of A corresponds to one and only one member of B. Just want to remind you, the abbreviation for if and only if is if, IFF. In simpler terms, we might say that for every x value, there is only one y value. So let's check out some examples. We sometimes diagram this with domain, x values, and range, y value boundaries. So in these problems, the domain is set A, and the range is set B. Let's look at number 1. Is it a function? Well, A goes to D. A only has one choice, always goes to D. B only has one choice, always goes to E. C, every time you put this sucker in, comes out an F. Is it a function? You bet your bottom dollar it is. Why? Each x value is paired with exactly one y value. If it's a function, that's always the reason. I'm just defining what a function is. That's what I'm saying why. Let's check out number 2. Actually, let's do number 2 together. Promise it won't be awkward. A, every time you put an A into the function, you get a D out. Every time you put a B in, you get an F out. Every time you put a C in, you get an F out. This also is a function. The reason it's a function is when you put a letter in, that letter only goes to one thing. Boom. Number 2. I'm sorry, that was number 2. Okay. Let's look at number 3. A. When we put A in, we have a choice. It could go to D or it could go to G. As soon as that happens, ladies and gentlemen, that makes this not a function. Why? Because point A is paired with two y values. Namely, D and G. Not a function. Number 4. Is this a function? Bet you. A goes to G, C goes to G. Both A and C have no choice. There is one path, and they both lead to G. So each x value is paired with exactly one y value. What is an easy way to determine if something is a function or not? Well, here's one easy way. If you're given a list of elements in the domain and range. If the range has more elements than the domain, then it's not a function. Or you could say, if the domain has less elements than the range, it's not a function. So looking at number 5, this fits that description. I guess it doesn't fit that description. So 5 doesn't fit the description of an easy way to determine it. The range has less than the domain, so it's a function. But you can still use the old-fashioned way. 2 always goes to 7, 0 always goes to 7, 5 always goes to 3. It's a function. Number 6, not a function. The range has 3 values. The domain has 2. The old-fashioned way, 2 has a choice. It could go to 7 or it could go to 3. Not a function. Number 7 is a function. The domain has 3 values. The range has 1. the range is less or equal to, then it's going to be a function. Continuing. Okay. What is a mapping? Notice the similarity between this definition and the definition of a function. A mapping, a correspondence between the preimage and image. Over here we said between two sets A and B, which was domain and range. This is between a preimage and an image. Is a mapping if and only if. We could also have said if each member of the preimage corresponds to one and only one member of the image. So let's talk about preimage and image. Preimage means the original image, and the image is after you've changed it in some way. So looking at number 8, first of all it says that the preimage is triangle J, KJ, KLM, which I could read. So this is the preimage, pi, this is the image. It's not really pi, just abbreviating. So is this a mapping? It is. Let me explain why. We don't know how these things are paired together, but there can be a correspondence. For example, maybe L corresponds to O. Maybe M corresponds to N, and K corresponds to P. There is enough points in the image, it's the purple one, so that the preimage, each of those vertices can go to a different point. So here's our explanation why. I'm going to take the explanation from the previous page and I'm going to change it. Instead of saying each x value, I'm going to say each vertex. And I'm going to say each vertex of the preimage. Actually, let me just erase this. Let's start over. Each vertex is where two of the segments come together, where they intersect. Each vertex of the preimage corresponds, or is paired with, to exactly one vertex of the image. In other words, if each of the letters from the preimage only has one choice, but to go to one letter to the image, just like with a function. All right, let's look at number 9. This one looks different. Is it a mapping? Is it not a mapping? Each of these cases, the preimage is the first one. So L can go to Q, K can go to R. What about M? M could go to Q or R. Does that still make it a mapping? It does. Because each of the letters in the preimage only has one choice for the image. So our reason why is identical to previously. If you want to put ditto marks for this, you have my blessing. This next one is not a mapping. Let me spoil the surprise. Here's why it's not. If L goes to T, and K goes to S, and M goes to V, there's going to be one point left in the image that nothing goes to. But it has to correspond to something in the first image. So pick one of the letters from the first image, doesn't matter which one it is, and it has to go to that one. And at that point, it is not a mapping because K has two choices. It could go to S, and sometimes it goes to U. Just like on the previous problems, looking at, let's say, this one right here, A has two choices. It could go to D or it could go to G. It makes it not a function. For this, it makes it not a mapping. Why? Let's be specific. No, we can't be specific because we don't know how this would be paired together, so let's not be specific. One vertex in the pre-image, that's the first picture, corresponds to two vertices in the image. Okay. Number 11. Is this a mapping? Pause this right now. Well, not right now. Pause it right now. Well, not right now. Decide if 11 is a mapping or not. Pause this. Unpause this. Was it a mapping or was it not a mapping? Let's see. L could go to T. K could go to T. M could go to T. This is a mapping. Each letter in the preimage, K, L, and M, they all only have one choice. They're going to T. So yes, it's a mapping for the same reason that it was before. Same question from the other side. What is an easy way to determine if something is a mapping or not? It's the same answer as it was before, but different terms on the other side. If the image has more vertices than the preimage, wish I would have wrote smaller, then it is not a mapping. Just do a little bit of this. I could get 3 P's. Well, one of them might have been backwards, a mapping. Once again, if the image, that's the second one, has more vertices than the pre-image, and it's not a mapping. So we look at 12, you can't just look at the pictures, you have to look at what you're told the pre-image is and the image is. So the pre-image is here, and the image is here. So in this case, the image has the same, or has less vertices, so it is a mapping. Looking at 13, this is the pre-image, this is the image, according to this down here. The pre-image has 1, 2, 3, 4, 5, 6 vertices. The image has 1, 2, 3, 4, 5, 6, 7 vertices. Well, that's one too many. Not a mapping. 14. Pre-image, according to instructions down here. Image, 1, 2, 3, 4 vertices. Image, 1, 2, 3, 4 vertices. Is it a mapping? Sure is. Okay. Not all mappings are useful. We don't want to start with a triangle and end up with a segment or a point after we map them. Ha ha ha. We want to study the mappings that preserve the number of points between the pre-image and image. In algebra, when there is exactly the same number of elements in the domain as there is in the range, it's called a one-to-one function. In geometry, that's this class, when you have the same number of points in the pre-image as the image, it is called a transformation. That is an important word. A transformation, once again, means that the pre-image and the image have the same number of vertices. Well, let me restate that. They have the same number of types of things, because the shape doesn't have to be a polygon. So if the first shape is a circle, second shape's going to be a circle. If the first shape is a triangle, second shape's going to be a triangle. If the first shape is a duck, second shape's going to be a duck. So check out one-to-one functions and transformations. So example of a one-to-one function. There are 3 elements in the range and there are 3 in the domain. Not a one-to-one function. There are 3 elements in the domain, but there are only 2 elements in the range. Both of these are functions. The first one's one-to-one, the second one is not. Looking at the transformations, or looking at these other mappings, I should say, these 2 are mappings. The first 2 are relations. Specifically, I guess those are function relations. So these mappings over here, if it's a transformation, if they have the same number of things in them. So the first shape, the pre-image, we'll assume it's the top one because there's no primes on it. It has 4 vertices, 4 segments. The image, the yellow figure, it's got primes. That means it's going to be the image. It has 4 vertices and 4 sides. That's a transformation. This last picture over yonder has a rectangle and a triangle. If the rectangle is the pre-image and the triangle is the image, this is a mapping, but it's not a transformation because they don't have the same number of points. Transformations and one-to-one correspondence functions. This is the same, these terms mean the same thing in different contexts. Transformations deals with geometry, one-to-one functions deals with algebra. A transformation is a one-to-one correspondence between the points of the pre-image and the points of the image. Okay. We will only be studying transformations. A transformation guarantees, money back guarantees, that if our pre-image has 3 points, then our image will also have 3 points. To sum up in large font with some caps and a little bit of bold, a transformation must have a pre-image and an image with the exact same number of points. That is the most important thing in this entire lesson. Number 15. Is this a transformation? No. There are more points here than there are here. 16. Is this a transformation? I don't know. There's so many points. Let me count them. 1, 2, 3, 4, 5, 6. Well, that green little fella better have 6. 1, 2, 3, 4, 5, 6, 7. No, not a transformation. Number 17. 1, 2, 3, 4. Let's go look at 3. Image. 1, 2, 3, 4. Transformation. Please do your assignment. Your assignment specifically is going to be section 2.2, practice worksheet 2. Thank you. Okay.